All right. This section, let's talk about linear equations. We're not first going to talk about the definition, and in the next and some properties, general principles of solving linear equations. And then next section, we will focus on how to solve it. Okay, so the definition. A linear differential equation. Actually, first order linear differential equation, given that we're still doing first order. But everything I'm introducing here actually does not focus too much on the first order part, but more about the linear part. Okay, so we're solving equations looking like this. That is y prime equals at times y plus a b may be a function of t. It's called linear simply because you have y prime, you have y term, and they are in linear terms, which is a constant times itself. You don't have y square, you don't have sine y, things like which is not linear. Like I said before, AT and BT can be nonlinear with respect to t. Because what we say about linear here really is with respect to y. All right, so very easy. Let's check this. 2y plus 3t squared. This is linear. Why? Because you have a y prime, you have a y, and you have a nonlinear term, but it's with respect to t, so it's fine. 3y prime equals 4y, 4t, y minus 2t squared. This is linear, even though you have a 3 here, and technically we don't have a 3 here, or a function of t here. What you can do is you can divide this one on the other side, so you still have the same form. Okay? And clearly, the logistic growth is not linear for the simplest one because it's y minus y squared, and this term is not linear with respect to y. Okay, so we will focus on this type of first-order linear differential equations from now on for the next 2 sections. And why do we have it? It's actually very common to see them in real life. I will give you some simple examples, and you will see more in your homework. Okay. So let's take y, and let's say we took a loan from the bank. Let's call it y, and it's a function of t. So as time goes by, you'll initially probably take $300,000 for your mortgage, but as time goes by, you're making monthly payment. Therefore, your loan, your debt, should gradually reduce. Okay. Now we have the interest rate. Let's just take a easy number, 1% per month. And then you take the monthly payment. Okay, and then probably $700. Okay, now we want to actually model a differential equation which your loan satisfies. It's pretty easy to do if you're thinking about monthly changing rate. The changing rate of your loan should go up because you're paying interest. So it should be 1% times your current value. The bigger the value, the bigger the interest you pay, minus what you just learned, what you just paid for the monthly payment. So this is easily a differential equation to approximate, okay, your loan value after each month. You plug in a different t if you end up solving it. You will have a different outcome. And from here, you can see this is easily linear with y prime, with a function of t, which is constant, and a function t which is a constant. So this is of a y prime equals at, y plus a bt case, where at and bt are constants. So this is linear. And many things in real life behave this way, especially you are involved with both the percentage gain or lose, and also a fixed amount of gain and lose. So that's why we want to solve them. All right. Now, how do we solve this linear system? We first want to talk about linear principle, not linear system, linear ODE. We want to talk about linear principle. We have done this linear principle before for matrix. Now I want to compare them one-to-one, so you can migrate your understandings about linear principles in matrix algebra to what we have for differential equations. Okay, so the first thing we want to talk about is something called homogeneous case. That is this. Okay. Moreover, this is separable. Actually, you can solve it. Easy to solve. Okay. So what you did is simply you just assign BT equals 0. So if you compare, this is a non-homogeneous case, and this is a homogeneous case, corresponding to this original ODE. That's called homogeneous. Okay. Now, what do you mean by linear principle? This is what we have. We have several ways of saying it, but basically we can say first in this way: if y1 and y2 satisfies, let's call this non-homogeneous case, N, and this is homogeneous case. Okay, satisfies the non-homogeneous ODE. Then y1 minus y2 satisfies the homogeneous ODE. Okay, let's translate it into a mathematical expression. That basically means if y1 prime equals AT y1 plus a BT, which means y1 satisfies the non-homogeneous case, and y2 prime equals AT y2 plus BT, and then you take the first equation minus the second equation. Now, of course, you have y1 minus y2 satisfies the non-homogeneous one because BT and BT cancel each other. Okay, which is roughly y bar prime equals AT y bar, where y bar is given by y1 minus y2. Okay, so let's go back to why do we want this? Well, the reason we want this is because when we solve a differential equation, we usually have a general solution, right? General solution means you have a lot of solutions. Now, what does linear property tells you? The linear property tells you that no matter how many solutions you have, just take any two solutions which both satisfies this, then the difference between them is going to be a solution that satisfies the homogeneous case. In other words, any solution of the non-homogeneous case is or can be written as y1, or let's say y equals yht plus ypt. Here, ypt is any one solution of the non-homogeneous case. P stands for particular, and this YH is going to be the general solution of the homogeneous case. So the general solution of any general non-homogeneous case where we have the linear differential equation can be decomposed into two parts. One part has no general in it. It's just one particular answer. The other part contains all the ones which will satisfy the other homogeneous case. That's where the general part, that's the harder part. But the nice thing is, to solve this harder part, you'll need to solve an easier equation, which is homogeneous, which means you don't have a BT. which is very easy to do because it's separable. Okay, so we kind of divided the task of a general solution for non-homogeneous case into two steps. The first one is general solution of homogeneous, which is hard, but easier than the original one, finding the general solution of the original one, because homogeneous case is easier than the non-homogeneous case. Okay, then finding one solution of the non-homogeneous. Which is again easier than the previous one, because the previous one you want to find all the possible solutions, but for this one you only need to find one. As long as you find one, you add it to this one. That's the point of the whole general solution of the original linear ODE. That's why we're using the linear principle, and all that thanks to if we take A minus B, we will have the difference satisfying the homogeneous equation. This only works for linear. Okay, if you have a nonlinear, simply something like this. For example, let's say we have a nonlinear differential equation. And we have two solutions satisfying both. Okay, the corresponding homogeneous is going to be this one with 0. Okay, so we don't write it. But if you take the first one minus the second one, you will not have you still have the homogeneous case, but the problem is your y1 minus y2 does not satisfy this. In order for that to happen, you need this. But now you have square, therefore you cannot have this. Okay, so not qualified for linear principle. Therefore, if you want to find the general solution of this one, you cannot take the D tool to find this one first, and then plus a special solution. It won't work. Okay, that's roughly the ideas we want to express in this section. That is, next time you see some linear differential equations and you want to find the general solution, we decompose the task into two things. Number one, find the general solution of some easier case, which is a homogeneous case. Number two, find only one solution for the particular case, and that's it. For the non-homogeneous case, that's it. Sum them together, you have the answer. All right, that's our principle. I don't know if it's easy or hard for you to understand, but now we can actually show you the principles that we have used multiple times before. So I gave you some analogies. The first one is actually taking the derivative. Solve y prime equals 2x. Well, everybody knows the answer is x squared plus c. Now wait a second. What do you exactly have? Now if you take this x squared plus c, okay, let's see, y equals x squared plus c. So what do? The first thing you do is you find a part which is x squared. You can also take x squared plus 1, doesn't matter, you just find 1. You didn't find everything. This is the yp, the particular one. For non-homogeneous case. Right? Then I should plus the one for homogeneous case. What is a homogeneous case? That is going to be the part such that y prime equals 0, right? You have 2x here, but I have 0 here. What's the solution for that? That's every single constant. That's y plus a c. So the general solution of this one is c, okay, which you put here. And this is going to be the non-homogeneous case, which you just solve for 1 instead of general solution. But if you put them together by adding, you find the general solution of this ODE already. Why? Because this is linear, so you can do this. Okay, that's the first example. The second example, let's go from ax plus b. In linear algebra, and let's take our a to be 1, 2, 2, 4. From here you can see the determinant is not 0. The determinant is 0, so you are not going to have a unique solution. Okay. How do you solve a linear system like this? Well, you have 2 steps. Remember, the first step is try to find a special one, and you can clearly see yp similar to y. Let's just not use a special solution. For the non-homogeneous case, which is 1, 1. How do you find it? Well, try your best. You plug in 1, 1, you can see it works. We will skip that. That's task 1. Task 2. What you want to do now is you want to find the solution for the homogeneous case. Try to recall what we had in linear algebra. The second job is try to solve this. Okay, so 1, 2, 2, 4. x1, x2 equals 0, 0. Of course, they give you redundant information. So x1 plus 2x2 equals 0. x1 equals negative 2x2. Therefore, the final answer is going to be negative 2x2. x2, which is a constant, times negative 2, 1. And we can rewrite this one to be a constant, general constant C. So again, you solve a particular solution. You don't need the general solution, just one. Okay, and that one is 1, 1. Worked. There may be others works, but I don't care. I just need one. Second job, go into the homogeneous and solve for the kernel of the matrix. And you got this. With a general constant, you actually have a one-dimensional, okay, solution space for the homogeneous case. So finally, what's your final general solution? Of ax equals b. That will be the part of ax equals 0 plus the part which is special. If you try to recall what you had in the linear algebra, this is exactly what you do, which is exactly what we just introduced. For differential equations also, a part for homogeneous plus the part which is not homogeneous. The part for not homogeneous, you only need one solution, and for the part for homogeneous, you need to find a general solution with the constants. Okay, why? Because matrix operations are also linear. That's why. Okay, so that we can do all this because it's a linear differential equation, or it's a linear matrix, or it's a linear operation for taking derivatives, given by the first example. This only works for linear. Some people will call this the kernel of A. So everything in linear algebra is connected to what we have here. If you think about it, it's very easy to think about, right? Basically, you start with some x, okay? And then you apply A. And then you, you receive B. Now what you want to do is you want to actually go to B and track what A is. That's what you mean by solving x for ax equal to B. So you are defining a function, and you will be able to do it uniquely if your function is 1-to-1. What you don't know is actually, when you take A, you erase some of the information, right? If this is the original thing, and this part is actually what gives you B, and everything else is actually what you erased. What do you mean by erased? That means if you do AX, it becomes 0, homogeneous. That means you erase x after you apply A. Then when you backtrack, you better backtrack the part to find one thing here, and then you better add the part that you erased. And how do you find where the part you erased? You go to the kernel, because that's everything you erased from there. If you take the derivative, for example, y prime equals 2x, what happened? Well, what happens is whatever constant you had before, if you take the derivative, you erase the constant. Okay, why? Because it's in the kernel of your operation, which is taking the derivative. No matter what constant you put in, you erase it because it becomes 0. Therefore, when you try to recover from 2x of x squared, you better add the constant that you erased. And the way to find the part you erased is, again, solving the homogeneous case. This is what's special about linear operators. But if you see what you have now, it's just like, what happens for solving linear equations. Doesn't matter if it's a linear matrix equation or it's a linear differential equation. It's the same. All right, that's all we have for 1.8. We will solve this type of equations in 1.9 using something called integrating factor.